In this video, we will talk about a specific equilibrium constant called the KSP, or the solubility product constant. And it's for dissolving solid. When we have ionic solids, they will dissolve into water. And always assume complete dissociation, even if you know it's not a very soluble salt. When it dissolves into water, it will separate into cations and anions. Remember that the cation always gets surrounded by the oxygen part of the water, and the anion always gets surrounded by the hydrogen part of the water. When the solid is first added to the water, no ions are present. But then, as the collisions occur, the water will pull that ionic salt apart. And again, always assume that the ionic salt is soluble. So it will at least split up into one anion and at least one cation. Your solubility rules, remember sodium, potassium, ammonium, and nitrate are all soluble. An example of writing a ionic compound dissolving is right here. We have calcium fluoride, CaF2. Notice that it is a solid, so there is its species, and it will split up into a calcium ion and two fluoride ions. Looking on the periodic table, we see that calcium is an alkaline earth metal, so it has a +2 oxidation number, and fluorine is a halogen, and all the halogens have a -1 oxidation number. And just make sure that it's balanced, so that's why you need to put a 2 in front of that fluoride ion. Now, when you first put it into water, not much happens, but over time it will come to equilibrium. When that happens, I can draw an arrow going backwards. So that means that the rate of the calcium fluoride dissolving will be equal to the rate of the calcium fluoride going back and forming a solid, or recrystallization. When we write an equilibrium constant expression, we have an equilibrium constant, and it's called the KSP, or the solubility product constant. And this solubility, it is an equilibrium position and it can be changed. And as I said before, a saturated solution is at equilibrium. Anytime you have a saturated solution, you're going to have a solid, a little bit of the solid at the bottom, and then some will be dissolved in solution. When you see that situation, that saturated solution, then you can assume that you're at equilibrium. And this means that no more solid will dissolve. And it is advantageous to have a lid on it. Otherwise, the water might evaporate. But this would be a saturated solution where you have the solid dissolving into solution at the same rate as it is recrystallizing. And it really doesn't matter the volume of water that you have. It's just that we want to make sure there's water in there. That's why we want a lid on there. But no matter the volume, the saturated solution will always have the same amount of ions dissolved. Or in other words, the molarity will be the same. Let's write the KSP expression for each of these following salts below. So first of all, magnesium bromide. To write magnesium bromide, I'm going to look at my periodic table and see that magnesium is a +2 and bromine is a halogen. And looking on the periodic table, I see that it's a -1. When I write the ionic salt, I need to have a neutral compound. So I'm going to have 2 bromines for every 1 magnesium. Then I'm going to put it into water and I get these ions. We need to make sure it's balanced, so I need to put a 2 in front of the bromine. And I'm going to make a saturated solution, or put it at equilibrium. So I need to have the arrow going backwards. So this is how that equation will look like. It's optional, but you can say that this is a solid, that's its species, and each of these other ones are aqueous. Now notice that we do not draw water. So even though they say magnesium bromide is put into water, you would end up with water on each side of the equation, and because of that, you can eliminate it. So even though it is dissolved in water, and we do see that the magnesium bromide is a solid, we don't draw the water part, or we don't write the water part. To write the KSP expression, I am going to say KSP, and because it's at equilibrium, we write this the exact same way that we have throughout this whole unit. It's going to be products over reactants. So following the pattern, I'm going to have magnesium with a +2 and the bromide ion raised to the power of 2. Notice that I have written the charges, so you can see that there's a -1 there and there is a +2 there. and that I have used the stoichiometry. And also notice that there is not a denominator. So it's just the products that go into your solubility product constant. So this is our formula. So later on in this goal, we are going to talk about how to solve for KSP. Let's, however, do one more KSP expression. So in iron 3 chloride, that means that I have iron is a +3 and I have the chlorine is a -1. When I put that together, I have an FeCl3, and then I'm going to make it dissolve in water, so I have the double arrows, and then I will have the ions. Make sure it's balanced, and there is my formula. Next, I will write the KSP expression, and let me just clear up some room. I will have for this one KSP times the concentration of the iron 3, so Fe3 plus times Cl minus raised to the third power. So this is how you write that formula. So let's do another one. We have calcium iodide this time. So I'm not going to include the solid in the equilibrium constant expression because we don't include solids. But I have the calcium ion times the iodide ion. And you can't see my charge. Let me write it a little bit better. And that is squared. So there's my formula. Now, according to Le Chatelier's principle, if we add more salt, what will happen? So if I add the salt to this, remember, add away, take towards, but remember that adding a solid to something at equilibrium does nothing. If you had this as a saturated solution, so I'd have a little bit of solid here at the bottom in my closed container, adding more solid, it would just sink to the bottom. That is not going to interfere with how much is dissolved in the water or how much is recrystallizing back, because it's going to dissolve and recrystallize at the same rate. So adding more salt, it does nothing. As far as solubility goes, it's affected only by temperature, the concentration of the ions, and what's called the common ion effect, which we will study in our next goal. Only the temperature changes the KSP. For a solid solute dissolved in liquid, increasing the temperature would increase the solubility, and so you would increase your KSP or have a larger KSP number. Whenever solubility is talked about with the KSP, this would be the concentration of the ion that you only have one of. So if I solved for the calcium ion concentration, that would be the solubility. Let's do a solubility product constant problem where we put the numbers in. So we have copper 1 bromide, and it has a measured solubility at a certain temperature. Calculate its KSP value. So we're going to solve for that solubility product constant. First of all, write a balanced net ionic equation. So I'm going to start with my copper 1 bromide, and then I'm going to split it up into its ions. Copper 1, that means that's the charge of the copper, and bromine is a halogen. And I just need to do my reversible arrow because it's going to be saturated. I can't put my species in, but it's not necessary as long as you remember you're starting with a solid. Then you're going to write your KSP equation, and then let's put our numbers in. And it says it has a measured solubility of, so that would be the concentration of the ion that there's only one of. And I happen to have both my anion and my cation are a 1-to-1 ratio. So this is going to be the concentration of both of them. And if you really think about it, when you put it into the water, it would split up into equal concentrations. They would both be 2 times 10 to the minus 4. So let's plug that value of solubility into my formula. And again, that's going to be the concentration of the single ion. And this one will also have the same concentration because they're formed at the same time. So then I just multiply this and I get 4.0 times 10 to the minus 8. And remember, there's no units. So there's my final answer. So again, here is my copper 1 bromide. And then it splits up into the copper ion and the bromine ion. So you see the concentration of one of them is going to be the concentration of the other. If this one is 2 times 10 to the minus 4, then this one's going to be 2 times 10 to the minus 4. Because they're formed at the same time. So there are two types of KSP problems. One is where they give you what the ion concentration is, and the other one is if they give you what the KSP concentration is. Let's go ahead and do that type of problem. So we have copper 2 iodate, let me write out the balanced chemical equation of it dissolving. And I just want to make sure it's balanced. So I do have 2 of those iodate polyatomic ions. Remember, if you have a polyatomic ion, it's usually surrounded with brackets, and they do not split up in water. Water's not strong enough to pull them apart, so they're going to stay together as their own little anion. Next, I'm going to write a KSP expression. So this is going to be my formula that I'm going to put my values in. And for this one, I don't know what the ion charges are. I do know that the KSP value is 1.4 times 10 to minus 7. I'm going to do a little ice table so you can see what the ratio of the ions are to each other. Because my solid is not in the KSP, I don't have to fill out this portion of the chart because it doesn't affect my equilibrium. My ions start out at 0, that's their initial concentration, and then the change, if this appears with plus x, this one's going to appear at plus 2x. Remember the stoichiometry. At equilibrium, this is going to be x, and this is going to be 2x. So that's what I'm going to put into my formula. So let's put those concentrations in, put in what we know, and I know this is 1.4 times 10 to the minus 7. And then we just figured out that this is x and this is 2x. Now I know it looks strange because I have a 2x here and I have it squared, but that is correct. That's what it looks like. That's the stoichiometry, and then that's the formula. So we're just combining it all together. Let's go ahead and do our math. 2x squared is 4x squared, and then I have 4x cubed. I'm going to divide each side by 4. To get rid of this x cubed, I'm going to take the cube root, or I'm going to raise it to the power of 1/3. So whatever your calculator does, I like to raise it to the power of 1/3 or 0.3333. So I end up with x is equal to 3.3 times 10 to the minus 3. So what does that x mean? So recall that the copper was the x and the iodide was the 2x. So I know that that is my copper, just the plain X. This is the ion that we only have one of, and so this is the solubility by definition. So if it ever asks you to solve for the solubility, then you just solve for X. Solve for the one that there's only one of. We do need to go back and do the iodate. The iodate is a 2X, so I just multiply 2 times what X is. So I have my solubility, or what my copper is right there, and what my iodide is 6.6 times 10 to the minus 3. So it's a little bit more complicated when you are not given what the ion concentrations are, but remember the stoichiometry. It will look this way. If I have a 1:2 ratio like this one is, the first one will be x, the second one will be 2x, and then you just put it into your formula, and it will always look like that. If I had a 1:3 ratio, it would look like this. I would have my x ion, and then I would have my triple ion raised to the cube, raised to the 3rd power. What does this KSP tell us? It tells us how soluble something is. If you have very high KSP values, that means you have a high solubility. So if you had something that was like a 1 times 10 to the minus 3, that's very soluble. So that means it's going to readily dissolve in water. If you had a very small KSP value, that would be like 1 times 10 to the minus 12. So now we're getting to it's not being very soluble. And if you had something that was to the minus 20, that's not very soluble at all. But remember, when you're doing these solubility product constants, you just assume that at least one of the ions will split apart. So you can write that solubility constant expression. If you're ever asked to compare solubilities, you can only compare solubility values for salts that produce the same number of ions. So looking at this table here, can you figure out which is the most soluble? And can you compare all of them? So looking through here, I see that we have silver iodide, and I know that this will split up into 2 ions. So will the next one, so will the next one. But that last one, it will split up into 3 ions. So we really can't compare that one to the other one. So we would have to be given more information. But I can compare those first 3 because they split up into 2 ions. And I see that this last one, this one is the least soluble. And the greatest number is that minus 12. This one is the most soluble.